Okay, on to part 2 of our discussion of mid-latitude cyclones. So you'll recall that back in part 1, we talked about how cyclones fit into the global scheme of things in terms of sliding the cold, dense polar air southward under the warmer air further south. And we also talked about the Norwegian cyclone model, which is a description of how cyclones usually evolve as observed down at the ground. But in the end, the Norwegian cyclone model is really just a descriptive model. It doesn't actually tell us why these low pressure centers form or why they amplify and get stronger. So in order to understand those kinds of things, we're going to have to start thinking about what's going on at upper levels as well. That is, we're going to have to start thinking about these systems in 3 dimensions. And so that's what we're going to do in this screencast. Now the starting point here is to recognize that the low pressure center at the ground in a cyclone typically has a corresponding trough at upper levels. And there's a particular configuration of the low pressure center and the trough that's going to allow this thing to grow. That is, cyclones that are amplifying, getting stronger, tend to always have the same configuration between the low pressure center at the ground and the trough at upper levels. So to sort of see how this works, let's sketch this out. So down here at the bottom, I've got a representation of what's going on at upper levels, say at 500 millibars. So this is the 500 millibar surface here, and then I've got the ground down here below it. And so these are both as viewed from above, so we're looking down from above at an angle. So sort of a perspective view. So now first, our low pressure center at the ground is going to be associated with a trough at upper levels. So first let's sketch in that trough at 500 millibars. So let's say the trough kind of looks like that. So that's our trough pattern in the height contours on the 500 millibar surface. Now for a growing system, the way this is going to work is that the low pressure center at the ground is always going to be shifted a little bit eastward from the trough at upper levels. So for instance, we might have our low pressure center at the ground over here, right? So the trough is over here, and we've got the low pressure center shifted eastward here of the trough. And of course, our low pressure center has the cold fronts extending more or less southward, and then the warm front extending more or less eastward, and then maybe we'll draw on a couple pressure contours here as well. So this is the typical configuration for a growing system. So we've got our trough over here, and then the low pressure center at the ground is shifted eastward of the trough. Or equivalently, we could say that the trough is shifted westward of the low pressure center at the ground. Now there's actually other terminology that we often use for this, and I should probably introduce it because I'm sure I'll use it as we go, which is that we typically refer to one side of the trough as the front side and the other side as the back side. And the idea is that the winds in this system are always blowing from west to east. Remember, the jet stream is always a westerly wind blowing from west to east. And so the front side then, the side that the winds are blowing towards, is over here. The eastern side of the trough is going to be referred to as the front side because everything is moving in that direction. And then the back side is this guy over here, the western side. So we can also say, using that terminology then, that the low pressure center is found on the front side of the trough, the eastern side of the trough. The front side of the trough is where the low pressure center is going to be found. And it's really this configuration. This configuration is key to understanding why these systems develop and grow. Now, the details of this are actually a little bit complicated, and I used to have this fairly complicated discussion of it in the notes, but in the end, I'm a simple man. I eat Raisin Bran. So I went ahead and simplified this quite a bit. I've got it down now to 3 simple pieces. If we can understand these 3 simple pieces, then we can basically understand how cyclones evolve. So the first piece that we need to understand And this one doesn't actually follow from anything that we've done before. The other two do, but this one is something I'm just going to introduce as being something new. And to be honest, I'm not really going to try to explain it because it's a little bit subtle. So I'm just going to state it as being true. And this first piece is that when you have troughs and ridges at upper levels, they have associated with them convergence and divergence patterns in the winds at upper levels. So troughs and ridges at upper levels have associated patterns of convergence and divergence at upper levels. And in particular, the way the pattern works is that generally on the front side of the trough, i.e., remember the front side is the eastern side, the side that things are moving towards, the front side. On the front side of the trough over here, we have divergence in the winds. And then on the back side of the trough, the western side, we have convergence. Now, as I said, I'm not really going to try to explain this. It's kind of subtle. If you want to understand this, you probably need to take more advanced courses. But this is how it works. On the front side of a trough at upper levels, we get divergence in the winds. And on the back side, we get convergence in the winds. So that's the first piece, the convergence and divergence patterns associated at upper levels with the troughs and the ridges. Okay, piece 2 that we need to understand this stuff. This is something that we can understand from what we've done before. And this has to do with the effect of the divergence on the pressure at the ground. So again, if we've got a trough at upper levels, so again, we're looking at a perspective view of both upper levels and the ground. And here we've got our trough pattern in the height contours at upper levels. And as we just stated, on the front side of the trough, we tend to have divergence. So the eastern side of the trough tends to have divergence. And we know from earlier in the course that if you have divergence at upper levels, that's taking mass away from the air column. Right? Divergence removes mass from the air column. And if you remove mass from the air column weighs less. And if the air column weighs less, that means the pressure is also less. So by taking mass away from the air column here at upper levels, we end up reducing the pressure down here at the ground. We end up decreasing the surface pressure below the region of divergence. So that's the second piece. Divergence at upper levels ahead of the trough removes mass from the air column, causing the pressure at the ground to drop as the air column begins to weigh less as you take mass away. Okay, that's piece number 2. Piece number 3 has to do with how the trough is related to the temperature of the air below it. And this, again, is something that we can easily understand from stuff we've done earlier in the course. So this just has to do with this relationship between the temperature and the thickness of the layer between the ground and 500 millibars, say. So you'll recall, so here I've got a sketch here from the side, so a vertical cross-section looking at it from the side. Got the ground down here, which is roughly 1,000 millibars, and then 500 millibars up here. And you'll recall that in the places where this layer in between is warm will expand, and places where it's cold will contract. So for instance, if I've got cold air here in the center, that means that this part of the layer is going to contract. And so the surface associated with 500 millibars is going to dip downwards over the place where the cold air is. But then we just have to recognize that a place where the surface dips down like this is just a trough. That's the definition of a trough. A trough is a place where the surface dips downward. And so as a result, what this is telling us then is that the trough tends to sit over places where the air is cold. And so if you look at this from above on a 500 millibar chart, it would look something like this over here at the right, where you've got a trough in your height contours. So this is a place where the layer is compressed because the surface is dipping downwards. And again, you'll recall that to see that the surface is dipping downwards, what you do is you go left to right. And as you go left to right, you start at higher height contours and cross down to lower height contours and then back up. So this place in the center is a place where the surface dipped downward, and the place where it dipped downward was over the cold air. Now, if that's true, then what would happen if we took the air here and we actually made it even colder? So if we had even colder air here in the center, then the layer would contract even more. And if the layer contracts even more, that means we get a deeper or a stronger trough at upper levels, a trough that dips down even more than it did before. And if we looked at that from above, as viewed on an upper level chart, it would look something like this over here on the right, where you have your trough pattern being more pronounced. Right? It's more curved here. It's more pronounced, which means you have a bigger dip downwards. It means you have a stronger trough. And now the last piece of this, which I don't actually have written on here, I probably should have written it on here, but I do have at least have it noted up here, which is that the stronger the trough is, the more divergence you have. So you'll recall that on the front side of the trough here, we have divergence. And the stronger the trough is, the more divergence you get. That should make sense, right? I mean, the divergence is associated with the trough. So the stronger the trough is, the more divergence you get here on the front side of the trough. So those then are our three easy pieces that we need to understand mid-latitude cyclone development. The first piece was that we have convergence and divergence patterns associated with troughs and ridges, and in particular, we have divergence on the front or eastern side of the trough. Second piece, and that's at upper levels. Second piece was that when we have divergence, it removes mass from the air column, which causes the pressure down at the ground to drop. And the third piece was this relationship between the air temperature and the trough. So the trough tends to sit over regions of cold air, and if it's even colder air, you get an even deeper trough. Okay, with those three easy pieces, we can start to put this together. And it goes something like this. So I'm going to go through a series of steps here, illustrating the evolution of one of these systems. And in each of these steps, I've got the same kind of figure here. I've got sort of a perspective view of what's going on at upper levels. We could say roughly 500 millibars, maybe a little bit higher. And then I've also got what's going on down at the ground in terms of the fronts down at the ground and the locations of the cold and the warm air. Okay, so again, this all starts, sort of our breeding ground for one of these systems is a stationary front. So it all starts with a stationary front, contrast between warm and cold air here. And at this stage, there's not really a whole lot happening, and there's not much happening at upper levels either. We do have a gradient in the heights at upper levels, as represented by the height contours, because you'll recall that where it's warm, the surface, the layer expands, so the surface is higher, and then where it's cold, it dips downwards. So we do have a general slope downwards from the warm side to the cold side, but other than that, there's not much going on. There's no disturbance at upper levels. But we do have the potential for disturbance because we have the temperature contrast. but in order to get it going, we're going to need something to kick it off. And typically the thing that kicks this off is actually at upper levels. There'll be some wave pattern that comes in at upper levels. So we start off with the surface with the stationary front, and then there's some wave disturbance that propagates in at upper levels. Now this wave disturbance was generally going to be produced somewhere else, right? So there's lots of things that generate waves in the atmosphere. I mean, there's storms in other locations, there's mountains, land-sea contrast. There's lots of things that can generate waves in the atmosphere. And so this is some wave that was produced somewhere else and then propagates in over this region of the temperature contrast. That's usually what we need to kick this off. Now, you'll recall that if you've got this wave disturbance at upper levels with a trough, on the front side of the trough, we've got some divergence. And that divergence is going to remove mass from the air column and cause the pressure to start to drop down at the ground. So that's the next step. We'll start to form a low pressure center down here at the ground. So you can think of this as being the transition to our frontal wave stage. We're just starting to form this low pressure center down here at the ground associated with this wave that propagated in from somewhere else. But once we've got some low pressure center, a low pressure zone down here at the ground, we're going to start to get some circulation around it in the counterclockwise direction. And so we're going to start to organize into cold and warm fronts here associated with the low pressure system. And then as time evolves, you're going to bring this colder air here on the west side, again the back side of your low pressure center. We're going to tend to bring colder and colder air here on the back side because up here to the north, we've got all this cold air, and as things are rotating in the counterclockwise direction, we're going to bring colder and colder air here on the back side of our low pressure center. So it gets even colder than it was before. And this is where that configuration that we talked about before between the low pressure center and the trough comes into play. Because the trough, or the low pressure center here, is on the front side of the trough because that's where the divergence was. Divergence here on the front side of the trough produced the low pressure center. But because the low pressure center is shifted eastward, the cold air on the back side is going to sit more or less underneath the trough up here. And remember, as we bring in colder and colder air on the back side here below the trough is going to get deeper and deeper because the layer between the ground and upper levels is going to contract, which is going to cause the trough to get deeper. So there the trough gets deeper. And as the trough gets deeper, as the trough gets stronger, that's going to cause the divergence on the front side of the trough to get stronger as well. So I just made the divergence a little bit bigger here. That's how I represented the divergence getting stronger. So before we had the trough like this, and then the trough got stronger because of the cold air at the ground, and that caused the divergence to get stronger as well. But if the divergence gets stronger, then that's going to take more air away from the air column, more mass away from the air column. And taking more mass away from the air column is going to cause the pressure at the ground to drop even more. So now the low pressure center at the ground is going to get stronger. As represented by showing more pressure contours and making the low pressure center, the L here, bigger. And then as the low pressure center gets stronger, you're going to have even more circulation around the low pressure center, which is going to bring even colder air here on the back side. And if you bring even colder air here on the back side, that's going to cause the trough to get even stronger. It's going to cause the trough to deepen even more. And if the trough gets even deeper, then the divergence is going to get stronger. And if the divergence gets stronger, it takes more mass away from the air column, which causes the pressure to drop, which causes the winds to get stronger, which brings more cold air here on the back side, which causes the trough to get bigger, which makes the divergence bigger. So you can see how this is going, right? There's a amplification cycle here going on here, where it's amplifying all by itself. So the different parts of the system are each amplifying themselves as it goes. The divergence amplifies the low pressure, and the circulation around the low pressure and the cold air amplifies the trough, which then feeds back on the divergence. And so then on it goes, amplifying just like that until the system finally occludes. So let's step through that again, because it's kind of a complicated process. So let's go back here. Back to our starting point. So again, our starting point was the stationary front, which has the potential to produce a system because we have the temperature contrast. But we need something to get it going. And typically that thing that gets it going is some external disturbance, some wave disturbance produced somewhere else that propagates in at upper levels. Of course, that wave disturbance carries its divergence with it here. So on the front side of that disturbance, we've got some divergence. That divergence removes mass from the air column. Removing mass from the air column causes the pressure at the ground to drop. So now we've got a bit of low pressure along our stationary front. Since we've got low pressure, the winds start to circulate in the counterclockwise direction, and it organizes into cold and warm fronts. With time, as this continues to circulate down here at the ground, we're going to take more of this air from the north and pull it onto the backside of our system, here to the west of our low pressure center. So we're going to get more and more cold air on the backside of the low pressure center due to the circulation around the low. Because of the way this guy is configured, that cold air on the backside of our low pressure center sits more or less right below the trough. And so the colder we make that air, the more the layer that contracts, and the more the layer contracts, the deeper the trough gets. And of course, as the trough gets deeper, the divergence associated with the trough gets stronger. Stronger divergence removes more mass from the air column, which causes the pressure at the ground to drop. Causing the pressure to drop, of course, makes the system stronger because you have a bigger pressure difference. A bigger pressure gradient means more stronger winds. Stronger winds means we bring even more cold air on the backside of the system. And that colder air is going to cause the trough to get even deeper. Causing the trough to get even deeper makes the divergence stronger, removes more mass from the air column, causing the pressure to drop even more, and on we go. We go through this sort of amplification cycle with the different parts feeding back on each other so as to make the system stronger. So that's how these mid-latitude systems develop and grow. Now you should keep in mind two things. First is that this whole thing, you'll recall, these mid-latitude cyclones, as they're evolving, as they're developing and growing, the whole thing tends to be moving off to the east or to the northeast. So this whole pattern, as it goes through this evolution, would be moving along into the east, in the east direction or the northeast direction, more or less. And as it does, it carries all of this stuff with it, because recall along the fronts in particular, you've got these strong temperature changes along the fronts, and you've also got your clouds and your thunderstorms and precipitation along the fronts. Over the low center, we tend to have a region of cloudiness due to the warm air being lifted upward as the fronts come together. So all of these things, all of these weather features are going to be carried along with this system as it evolves and as it moves towards the east or the northeast. Now, the second thing to note is that this doesn't go on forever, right? The system can't amplify forever. And the thing that eventually kills it off is that eventually this cold air associated with the cyclone is going to wrap all the way around. That is, the cold front's going to catch up with the warm front and the system occludes. And once the system occludes, as represented here, right, where the cold front has caught the warm front, at that point, the low center is completely surrounded by cold air. It's cut off from the temperature contrast. The temperature contrast was what was driving all of this. And so at this point, it's going to start to decay. And eventually, the low center will actually detach completely from the frontal zone. And at that point, it's pretty much just died off. Okay, so that's pretty much how it works. It's a little bit complicated, but that's how the evolution of these low pressure systems work. And in the next screencast, we'll go through and talk just a little bit about what some of these low pressure systems looks like, just in terms of a few examples.